Welcome to Module 3. In this module, we're going to use the instrument for testing unknown samples, just as you will for your application. Although we cannot practically expect to demonstrate every type of sample you may encounter, we will measure several typical examples of samples that represent the most popular applications. The measurement procedures and evaluation of results will be similar, even if your particular samples may be quite different. If you do have unique needs that are not covered by this module, please refer to the user's guide or contact your local Niton Analyzers sales representative for assistance.
We will start with the alloy application. When we complete the boot up procedure, the analyzer returns to the last mode used. For this demonstration, we will assume that the last mode used was the universal all-alloy chemistry mode. If so, we may simply press the test icon and proceed to measure samples as soon as the detector cooling message disappears from the display. For measuring in the more specialized alloy modes, such as signature match, superchem, or pass-fail modes, please refer to your user's guide or contact your local sales representative.
The all-alloy or chemistry mode is used predominantly for alloy analysis applications. This mode is used by all types of industries for all types of metal alloy families that can be measured by Thermo-Electron's Niton Analyzer. Our alloy customers range from the metal mining industries to alloy producers to alloy distributors and to users such as petrochemical and aerospace companies, inspection companies, government agencies, and ultimately to the end-of-life recyclers of alloys. We're going to show you measurements of several alloy examples that cover each of these categories.
Let's begin with a typical alloy sample that might be checked by the QC department at the producer of stainless steels. One of the most popular stainless steels in the world is this grade 316, an austenitic stainless, also known as a chromium nickel stainless steel. We will look at the results as if it were an unknown, but later we'll compare the measured results to the certified values. This will help to demonstrate that your portable Niton Analyzer is capable of providing lab quality accuracy for alloys.
We place the analyzer measurement window on the alloy sample, then pull and hold the trigger for say 5 seconds. As you can see, the analyzer identified this sample correctly within 1 second, and as we continue to measure, the chemistry results are being updated about every second during the measurement. The results will continue to become more precise as we measure longer. At the conclusion of the measurement, we release the trigger and the final calculation is displayed. The identification, or the ID, of the sample is automatically determined by the analyzer. It compares the analyzed alloying element values to a library of about 350 alloy grades in a table stored in the analyzer's memory. Each alloy grade has a lower and an upper limit set for the range of allowable variance in the recipe for that alloy. These limits are industry standard values, and most, but not all, are based on the Unified Numbering System, or UNS, specification for the alloy. Below are the minimum and maximum values for 316 stainless steel.
Note that the sample name or ID display is followed by the quality of match or confidence number, in this case a 2.3. This number can range from 0 to 10, with 0 being a perfect match and 10 being a distant no match. A no match will occur when the calculated confidence number goes over a factory default value of 4. For matched alloys, values between 0 and 4 show the degree to which a sample's makeup differs from the mid-range of the alloy grade's chemical content specification. Between 0 and 2 implies a match, 2 to 4 a possible match, and more than 4 a no match. An asterisk will appear next to any elements that are out of range. Alloy producers will typically use the minimum allowable amount of an expensive element in an alloy recipe and the maximum amount for inexpensive alloying elements. So do not expect all alloying elements to fall in the mid-range. In other words, don't expect a match number of 0 very often. Remember, the match number is based on comparison to the standard UNS alloy values in most cases.
Now let's look at the chemistry that was determined by this measurement. Note that the left-hand column contains the element symbol. The middle column shows the concentration result, and the right-hand column indicates the 2 sigma standard deviation, also called error or precision of the measured concentration. This 2 sigma value represents 95% confidence that the calculated values will be within the lower and upper limits set by the 2 sigma boundary values. 95% confidence implies that if this same measurement was taken 100 times on the same sample for the same length of time, 95 times out of 100, the measured chrome concentration would fall between 16.15 and 17.25. This error value is taken into account in calculating the ID confidence number. Another example is the value for nickel. Note the analyzed value is 9.69%, and the precision of measurement is plus or minus 0.7%. Similarly, moly shows both analyzed concentration and calculated precision values. It is so important to be aware of the precision of measurement that I often tell new users that no concentration number has any quantitative meaning until we know the associated error.
Now let's look at the effect of measuring time. Instead of holding the trigger for 5 seconds, as in the last shot, I'm going to do a 20-second test. What you will see is a more precise value for every element by twofold, 1/2 the error. The rule of thumb that we are demonstrating here is that the precision doubles for each 4-fold increase in measuring time. Okay, let's compare the values for the 2 shots. Here we see chrome for the 20-second shot at plus or minus 0.3% precision, and for the previous 5-second shot at plus or minus 0.55%, or about double the precision for the longer shot. The same will be true for nickel, moly, and iron, as we see by the chart below showing the 2 readings.
The Niton analyzer has so much greater accuracy and precision than the allowable tolerance in the typical alloying min-max specs that even the higher error associated with a 5-second shot is almost always sufficient for a quick and accurate ID. However, for comparing chemistries to a certified value, we suggest at least 20 seconds or more of measurement time. We can see the reason for this by comparing the certified values for this 316 standard to the calculated values based on the analysis results shown here. I'll read the certified values while we view the analyzed values for both the 5 and 20-second shots. Moly, 2.41%. Copper, 0.34%. Nickel, 10.25%. Iron, 67.52%. Manganese, 1.76%. And chromium, 16.68%. Clearly, the 20-second shot is more precise and therefore higher confidence in the displayed value and statistically better accuracy of analysis.
Although most producers of alloys need little or no sample preparation on new alloys with clean representative surfaces, it might be good to bring the subject up in the event there is an exception, such as a shot-blasted surface, a scale, a coating, a plating, a painted, or any other non-representative alloy surface. In this case, be sure to grind the surface down to the clean, bare alloy metal. The surface measured should always be the intended target material. Whatever is on the surface is what the instrument will measure. A portable grinder we have found to be useful for the field work is the Makita 9500, which you can find at www.makita.com.
Remember also to select an appropriate abrasive. Don't use zirconium oxide grinding paper if you're analyzing for minor amounts of zirconium, like with some aluminum alloys, 7050 for example. Some light elements in alloys like magnesium, aluminum, silicon, and phosphorus can't be determined without the use of an alternate model called the helium purged analyzer. When using the helium purge equipped instrument, don't use aluminum oxide grinding paper on an alloy that will be analyzed for low levels of aluminum alloying elements, or silicon oxide grinding paper when low amounts of silicon alloying elements are to be determined.
Okay, now let's do a typical petrochemical alloy, a so-called chrome moly steel, such as the 5-chrome half moly. Many refinery pipelines are constructed using this alloy. Typically, the primary goal of the testing in the refinery is to verify the correct alloy grade, so we'll test for just 5 seconds. Note that the ID is obtained long before the 5 seconds has elapsed, assuring the technician that the analysis is routine and the results can be reported with high confidence.
An example of a more challenging analysis would be the testing of the nearly twin alloys of 304 and 321 stainless steels. These two alloys have overlapping specification ranges, with the exception of a fraction of a percent difference in the titanium content. Titanium is added to 321 as a stabilizer for withstanding certain corrosive chemical environments. The petrochemical industry must be able to accomplish this difficult alloy separation in order to have absolute confidence that the correct alloy grade is applied to the intended use. A standard alloy analyzer requires longer measurement time to obtain enough statistical confidence or precision to correctly make this identification.
Here, for example, is a 321 titanium stabilized stainless steel that we will shoot. When only 321 is displayed for several seconds, we can stop the test and document the alloy ID. The same will be true for the other nearly twin alloy 304, which has no titanium added. Of course, a zero concentration level is harder to quantify than even a fraction of a percent, so it may take slightly longer to drop the second choice, 321, in the case of the 304 analysis.
Now let's take an example of the alloy recycling application. In the alloy recycling application, we may run into just about any alloy that was ever made. It's therefore typically expected that the instrument operator have good knowledge of alloys, so that interpretation of results can be accomplished when called for. With somewhere around 50,000 alloy grades in worldwide use, the scrap sorter's job can be demanding. Users in the alloy recycling industries will encounter non-representative surfaces, undersized samples, sharp turnings, shavings, grindings, filings, sweepings, wires, rods, highly magnetic materials, and every imaginable shape, size, and grade of alloy. Thermoelectron's Niton analyzer is smart enough to deal with almost every situation, but there will be a few examples of alloys that cannot be handled without combining the analyzer data with knowledge of alloys.
For this reason, we will measure several types, shapes, and sizes of alloys to demonstrate the use of the analyzer for this application. We will start right off with some tough examples. Here is a 1 mm 347 stainless steel wire. Okay, the test result is 347 stainless steel. So we see that the analyzer is smart enough to compensate for undersized samples down to about 1 mm.
So how about a thin foil? This copper alloy foil is a good example of a very thin foil. It's CDA 260 cartridge brass. It's about 0.2 millimeters thick. Note that again the analyzer has compensated for this thin sample, and it correctly IDs the alloy and gives its chemistry. This correct call will be the case for thin samples down to about 0.1 millimeter thickness, assuming that they cover the entire measuring window.
Now let us demonstrate an example of an incorrect measurement procedure. Instead of measuring the 347 wire in the test stand, as before, let's shoot it on the table. Since the measurement area is 1 by 2 centimeters, and this area is not completely covered by the alloy under the test, we therefore include the table in the analysis. With the table analysis being added to the wire analysis, we obtain a wrong result. Aluminum alloys of any size or shape are a special case and should be undertaken only after your sales representative has provided specific training.
As we said previously, the instrument operator will still need to be alert and able to make good judgments in cases where the sample is not clearly representative at the measurement surface, or it cannot be fully analyzed for all alloying elements. Some surface coatings are not obvious because they are similar in color to the alloy, for example. Examples are silver or cadmium metal coatings that might look like the alloy itself. Some examples of the need for a judgment call on the part of the operator will be given next.
Here is a sample of a bolt that when measured initially reads a mixture of steel and zinc. This is a material that has a zinc coating. Notice if I measure at the end of the screw where I have ground the surface, the reading for zinc drops dramatically. Since some of the signal is still received from the non-ground portions of the bolt, we still note some small zinc reading. The alert alloy sorter we'll know that the steel alloys don't contain zinc. Therefore, the conclusion is that it must be coated and we should grind the sample prior to its analysis. We can also notice a slightly off-color yellowish tint to the coated area that is not typical of a clean steel surface.
Another example is measuring this shot-blasted titanium alloy with and without grinding. Here is the shot-blasted surface. Notice the erroneous iron reading in the area where we have not ground the surface. Here now is the ground surface. When we measure in the area where we have ground the surface clean, we see a correct reading with no iron content. You can see the difference in the surface where the shot blasting has muted the shiny surface and caused a little bit of dimpling in the surface.
The reason the instrument is smart enough to correctly measure these samples of all shapes and sizes, assuming the surfaces are representative, is that it automatically performs what is called normalization on every reading. This means we force the analyzer to total all detected elements to 100%. When measuring undersized parts, the signal is reduced for all elements proportionately, and we can therefore use a ratio of the measured elements to normalize the result to 100%. However, this huge benefit has one minor drawback. A small percentage of alloys contain significant amounts of non-detectable elements, more than about 0.5% for example. In these cases, the instrument will normalize to 100%. So, if we have a copper alloy with the alloying content comprised of non-detectable elements, such as 10% aluminum, the reading will be normalized to 100% copper, the only detected element.
An example is the measurement of a copper alloy, CDA 642, which is an aluminum silicon bronze. This alloy is composed of copper with a combined total of about 9% aluminum and silicon alloying content. Without a special helium purged instrument, contact your representative for details, aluminum and silicon cannot be detected. Therefore, the only element determined is copper, and it reads a normalized value of 100%. However, the alert operator will notice that the color of the alloy is yellowish. With pure copper, it's clearly only red. Since CDA 642 is one of the very few copper alloys that have no other detectable alloying elements, and in fact it only contains non-detectable alloying elements, we can reasonably make the judgment call that this is CDA 642 based on the color.
Let's now switch to a specialized optional alloy mode called Precious Metals. First you will hit Navigate, and then Mode, and then Alloy, and finally Precious Metals. In this mode, we can analyze for metals and alloys of gold, silver, platinum, and other such precious metals and alloys. Here, for example, is a ring which is made of 14-karat white gold. We see the results show the content of gold plus each alloying element, in this case copper and nickel. Each carat of gold is 4%, so we divide the result for gold, 57%, by 4, and we have a value of 14 carats gold content. This precious metals analysis mode is useful for jewelry dealers, precious metal producers, and reclaimers of precious metals. This mode can be added to existing thermoelectron Niton alloy analyzers. If you would like to add this mode to your instrument, contact your local representative for pricing and details.
Okay, let's switch modes to electronic application. Another popular application is screening of electronics for restricted substances. This is for compliance with the EU's RoHS regulations, for example. Restricted substances are elements which can be toxic, such as cadmium, lead, mercury, hexavalent chromium, and brominated flame retardants. The normal electronic application adds a second mode to the alloy mode called the plastics mode, used for non-alloy type samples. The first step, then, is to select the appropriate mode for measurement. If we are interested in screening for restricted substances in solders or metal alloys used with electronic parts, we can leave the instrument in the alloy mode. Solders can then be measured like any other alloy.
Here is a typical tin lead solder called 6337. It is composed of very heavy, dense elements and is quite thick so that it will absorb all radiation from the analyzer. Therefore, we can measure this sample on the table without any concern of interference from the table. We see that it is identified correctly in just seconds, and we see the nominal 63% tin plus 37% lead. An example of lead-free solder is this SAC 305. However, this alloy does not cover the window, so we must not hold it with our hand.
Now to the electronics plastics mode. Press Navigate, Mode, Bulk, and Plastics. We use this mode to screen for restricted substances in all electronic parts other than solders and alloys. Examples are this printed circuit board or PCB, which we will test using the portable test stand. The most likely source of a restricted substance in a PCB is typically lead in solder joints. So I'll take the first measurement with these solder joints located directly over the window. Sure enough, we see high levels of lead, well over the allowable level of 1,000 parts per million,